Okay, so we're going to be talking about the events happening at the glomerular capsule and how filtration takes place from the blood into the capsule for urine formation. And I went ahead and started drawing the structure itself. Of course, here in yellow is basically the urine that's being formed in this tube, which is actually the proximal convoluted tubule. So let me add that here. The proximal convoluted tubule. All right. So there are the proximal convoluted tubule is here. This would be the actual capsule here itself, and we have a parietal layer and a visceral layer of cells. The parietal layer has more of cuboidal cells, so this is the Bowman's capsule, we call that. The Bowman's capsule has a parietal layer that are more cuboidal, and the visceral layer has a more squamous cells. And the visceral layer is the layer, so inside of that capsule, there is an inner layer that happens to be stuck on the blood vessel that's coming into that capsule. So the blood vessels are coming into the capsule, and actually it's a whole tubing that kind of goes around and around and then comes back out. So I only drew one vessel going in and then out, but it's really a long tube that kind of coils in there. But that tube is covered with cells from the capsule, which would be the visceral layer right here. So as the tube comes in, it's actually in contact with nothing other than the cells of the capsule, but those flat cells that are basically hugging this blood vessel. So the blood vessel is coming in, and we call this particular portion of the vessel the afferent arteriole. Afferent, A for arriving, and then it's going to coil in that Bowman's capsule, the glomerular capsule, and then it comes out as the efferent arteriole. So E for exiting. That's kind of how is a good way to remember them. And of course there's blood flow here, and the idea is we need to excrete everything that has to be we need to push it out of the blood vessel so it can be excreted into the urine and out the body. So as the blood is coming down here, let me switch colors. As the blood is coming down here, there's a certain pressure from the flow of blood here, and this will be called the glomerular blood hydrostatic pressure. So the blood is coming here and it's going to be pushing on this wall, and as it's pushing on this wall, it's allowing for fluid to seep out of the vessel and into the glomerular capsule. So here in red, I'm going to draw here the acronyms in the color I'm using them. So the glomerular blood hydrostatic pressure. So I don't have time to, or really the space to write it all out, but you can rewind the video and hear that. So the glomerular blood hydrostatic pressure. So that's one thing. So that pushes a fluid out. But there's also fluid in the capsule itself, and this fluid is also exerting its own pressure against the same wall. And this, I'm going to illustrate it here with my yellow arrows. So this would be the capsular hydrostatic pressure. Capsular hydrostatic pressure. So that's the pressure that is exerted from the fluid inside the capsule that is pushing against that that dividing wall. So the capsular hydrostatic pressure. And then in addition to that, you have these large proteins that are always carried in the blood vessel, and they can't get through the membrane. They are too large for a passage in the membrane, but they create this concentration of large proteins in the blood vessel, and they're creating an effect of osmosis towards them. If you have an area of highly concentrated proteins that cannot move, it's the water that's going to move towards them to compensate for that. So the presence of these large proteins create this additional pressure called blood colloid osmotic pressure. Blood colloid osmotic pressure. So because of these colloids, these large proteins, you have osmosis. So this is osmosis happening because of the presence of these proteins in the blood. So you have osmosis taking place, you have the capsular hydrostatic pressure from the fluid that's already in the capsule, you have both of these, but what you need is you need the glomerular blood hydrostatic pressure, right, from the blood arriving. You need that to be higher, stronger than the other two combined to be able to push that fluid out of the blood and into the urine. Because that's the purpose here. The purpose, we are in the kidneys, the purpose is to have blood filtrated in the kidneys. So all of that blood is coming with ions to be excreted, and really also just excess fluid or whatever it is. It needs to go, whatever that needs to get excreted in the urine needs to get out into the urine. So you need that pressure to be strong enough to compensate for the other two that are there kind of automatically, because these proteins are always in the blood. And as soon as you have liquid fluids on this side, you're going to have that pressure. So you need that blood pressure to be high enough. Now, to monitor that pressure, we have cells from the distal convoluted tubule. So I'm going to use a black color to basically show this is part of this system, but this is the proximal convoluted tubule. And if you go into your kidney anatomy, the tubule continues down, and there's the whole tubular system, and it ends with a distal convoluted tubule that basically comes back, swings back towards the afferent arteriole, and that's what I'm going to draw here. So this is the distal convoluted tubule that swings by near the afferent arteriole, and I'm going to draw this. So this is a tubule, and this is made of cuboidal cells lining the tubule. All right, so imagine this is really just a tube. However, in this portion of the tube, the portion that is the convoluted portion that kind of goes out and kind of comes next to the afferent arteriole, think of it as this is the part that comes and checks on the afferent arteriole. This is where we're going to have very specialized cells right here that are part of what we call the Juxtaglomerular Apparatus. So we have just regular cells on this side, but on this side we have really specialized cells. So they're a bit different in shape. So I just drew them a bit kind of larger here, different than the regular cuboidal cells that just line a regular tube, right? And this is tubing that still contains the fluid that makes up urine. So I'm just going to draw the fluid here to show you that this is the continuation of what we started with at the proximal end. So this is the distal convoluted tubule. So distal convoluted tubule, and we have this Juxta glomerular apparatus right here. These cells so we really call this series of cells macula densa. Macula densa, and it's in conjunction with this with this structure here. All of this is called, in conjunction with next to the afferent arteriole, all of this is called the Juxtaglomerular Apparatus. So this is the apparatus next to juxta, the glomerulus. So the Juxtaglomerular Apparatus is this collection of cells. So I'm just going to draw them like that. This is the macula densa part of the apparatus. And these cells are there to monitor the blood pressure. When there is pressure here, they're monitoring the levels of sodium ions, chloride ions, and really also water, so blood volume, and all of that is going to have an impact on the blood pressure. So these cells are monitoring over here. So maybe I can like draw this kind of arrow to show you that there is some kind of monitoring going on to see. Here I'll draw chloride ions, sodium ions, water, So these cells, this is what they're monitoring. And if they sense that there is a drop in blood pressure, for example, if there's a drop in water, right? Because they are monitoring water, right? Water. So if there's a drop in volume of water, there's going to be drop in volume of blood, because water makes up the blood volume. So a drop in blood volume means that you're going to have less pressure going down the hose, so down the blood vessel. So for these cells, a drop in water volume is an indication of a drop in blood pressure. So in response to a drop in, I'll write it here, if there's a drop in water, which will then be blood volume, right? Because they're linked, since blood is an aqueous environment, and if there's not enough water in your system, you're going to have less blood volume. So a drop in blood volume is basically an indication that blood pressure is dropping. And a drop in blood pressure is going to stimulate the release of renin. And that's really the purpose of this diagram, is to show you the relationship between the glomerular capsule and the distal convoluted tubule with its juxtaglomerular apparatus over here. These cells are very specialized cells that are monitoring what's coming in, because they want to see if there's a problem with the pressure here. If blood pressure drops, what could be the problem? Right? If blood pressure drops, can you see if there's a problem here? The problem is that this glomerular blood hydrostatic pressure is not going to be enough to have a net filtration of the fluid into the capsule. Remember, this has to be higher than the other two pressure to make sure that we're constantly pushing fluid into the capsule and creating that urine. If there's not enough blood pressure coming down the afferent arteriole, we're not going to be able to compensate for these other two pressures in the opposite direction. So we need the blood pressure to be strong enough to be, at least higher than the other two combined, to have a net filtration of the fluid into the Bowman's capsule. And that's where renin is released as a response to the blood pressure dropping.